Hello? No. Hello? Yeah, right, it's working. Is it loud enough? I mean, can you hear it? Yeah. Okay. Nice. Okay, so welcome back. Hope you had a very beautiful weekend and relaxed, ready for tough work. So, this week we will discuss interactions between populations. Okay. So let us begin with general thoughts about interactions. So we have to differentiate between I think it's a battery problem. Yeah, it's working. But it will stop in a minute. But okay. But let's see. Okay. Let's see.
Hello, test.
So, okay. What was I saying? Okay. So we will think about interactions. It's working? Yeah. Yeah. Okay. For populations, and we will begin with two populations. Okay. And obviously, in nature, you have networks of interactions, but we want to isolate the main characteristics of interactions between two. And actually, this is a way to proceed further if we want to have more, is to consider the main interaction between pairwise interactions and then construct networks of interactions which are all of them pairwise. Competition, predation, mutualism, or whatever. Okay? So the central point will be two populations interaction, and let's say one of those populations is A, other populations I call B, and I will make a kind of classification which is very general, okay, which will be based on the effects of the interaction on the population size. Okay? So if the interaction is such that is detrimental for species A, I'll put a minus here, so it's detrimental. The fact that B exists depletes the population size of A. And now let's say it is symmetrical in the sense that B also gets depleted. They are mutually depleting. Okay? So that's what we will call a competition. So, but maybe A is favored by the competition. Maybe it increases at the expenses of B. So that could be the case that the interaction is such that the population A gets higher increase rate when B is present, but B gets depleted by the presence of A. And so this I will put in this way, predator-prey. Why? Because it's a little bit jargon. Because it's not necessarily, because predator pay is usually referred to an interaction that happens at the level of the individuals, which results from the consumption of an individual of species, in this case B, by individuals of the species A. That's real predator prey without any marks. Okay? So, but there are other interactions that may be beneficial for one and detrimental for the other without having direct consumption, which for instance is host parasitoid. And you have a parasitoid, it needs the host, it actually will kill the host, but it doesn't feed on the host. I mean, it feeds internally, that depends on the stage of the, but it's from the biological mechanism is a little bit different at the level of the individuals. But at the level of the populations, it's pretty much similar. So this would be host parasitoid. So in general, we would say that's antagonistic. Okay? So the good word, if you want to be more formal, and you should say antagonistic interactions. Okay? So finally, there's the obvious case in which both benefit from the interaction, which would be mutualism. And again, this is a general word which hides a lot of biologically different interactions. For instance, you can have true mutualism. True mutualism, an example would be birds and flowers. Okay? So birds feed on nectar but also pollinate. So this is the classical interactions. There's also classical interactions with coral reefs and so on. But there are also interactions that are not exactly like these ones. For instance, symbiosis. Symbiosis is usually like you have a symbiont. It's a microorganism maybe which lives or grows inside of a higher order organism, and it's beneficial for both of them and gives you protection against something and so on. So again, there's a lot of biological diversity behind all of this. Okay? Now you could be there are limit cases like positive zero, okay, which is called commensalism. Anybody has an example of what could be positive and indifferent for the others? Any idea?
Fish that eats from the detriments from like sharks?
Yeah. For instance, yeah, the shark, it's metabolic, some organism that consumes metabolic waste from others, for instance. Other cases also. Any other case?
Aposematism.
Huh?
Aposematism, when the animal appears to be similar to another, and like the false coral snake and true coral
or
snake.
like with butterflies also, yeah.
It benefits in the way that the true coral is venomous, but the false.
But I don't know. I don't know anything about the snake. I know more about what happens with butterflies, which also can have mimetism. Yeah, mimetism. Okay, but mimetism is not necessarily neutral for the other species. Okay, so say I'm the species number 1, and then there comes the species number 2, and it's mimetic with me because it's trying to escape from some particular predation. So it's just getting But this can also be positive for the first species because can dilute effects of other predators. Okay, so could be, but not necessarily. Okay? So one very classic thing is also you have animals that are like mammals, and there are small, either insects or small animals, insects or whatever, that can ride on the, and so they are taken from one place to the other, that they would not be able to do over distances. And well, the mammal just doesn't care, has some small friend on his back. Yeah?
Another one which is neutral and positive would be something like trees, which can offer shelter or nesting ground to some animal, but that animal isn't really a pollinizer or a carrier of its seeds, so it's neutral for the tree.
Yeah, it could be. If the animal does no harm in this case.
Yes.
Yeah, it does not do that. Because there are interactions where a tree can give shelter to another species of plants. But this is usually antagonistic, because this plant will grow and deplete the resources for the first one. So that's a kind of situation which is interesting, which gives me the opportunity to say that, well, it's not that species have fixed interactions necessarily. Sometimes they have, but can depend on life history. So, for instance, if you have this big tree which gives shelter, it's called nursing for smaller individuals of another species. Okay, it's in principle, it's commensalism. It's positive for this species, but it's whatever. No effect on the first species. But if this one grows, then it will deplete this one, and then the interaction will be of competition, negative. So they can change sign depending on life history. I mean, if many times it's not. I mean, I don't mean that lions and zebras may change the the interaction, but with the species that have a more complicated, more complex life history, which have stages, different stages of life, there can be many different interactions. Yeah.
There is the example of the fig trees, right, that grow upon another tree, and in the beginning they are just like normal epiphytes, and eventually they grow and strangle
for instance,
the tree.
Yeah, exactly. So this is are cases where you have the change of interaction due to life history. Not necessarily. I commented on ontogenetic shifts, which is when you have really very different stages, like eggs, and then you have the fish and so on. It's an ontogenetic shift that obviously the interactions of the eggs will be different from the interactions of a big codfish. Okay? So interactions may change, and you should, be aware of this. But anyhow, so today we want to concentrate on this, on competition. And if we finish today, tomorrow we go to predator-prey, and we will skip mutualism, because for two species, mutualism, we can already, without any equation, know what will happen for two species. Pepans. I should have told this. Mutualism has some particularities, because there are obligatory mutualism and facultative. If it's facultative, it's very simple. You have species A and species B, then they could in principle grow up to their carrying capacities, okay? Without interaction. The interaction just makes them have more for both of them. So there will be a new actual carrying capacity, and they will be live in peace forever. Okay? So no need of equations if you have facultative mutualism. So no fun for the dynamics. But well, if you have I think you are it's okay. So yeah, if the mutualism is mandatory, it's a little bit different. But analyzing this with only 2 species is not so interesting, because what is interesting is mutualism in networks, where you can have the facultative and mandatory, obligatory interactions, and then they have other interactions with predator, prey, and so on. So then that really becomes something more interesting and had some dynamics which is not trivial, because the one I just told you is trivial, it's just growth. Yeah? So, okay. So, we will not use develop theory from 2 species mutualism in this course. Okay. Now, where's the? Okay. Now, let's think about competition. So, competition. Okay. Question: how do you think species can compete?
They both need to the same resources, so.
Yeah, okay, that's the classical, the same resources. Yeah. So resources are limited, okay? And some of the individuals will, I mean, there's different kinds of resource competition. You could have competition where the resource is equally divided between the individuals of a population, or sometimes not. It's not dividable, and then some individuals will not find resources, will die, and sometimes it can be divided within the population. It usually will affect fecundity, but I mean, we don't want now discuss all of this, but just to have an idea that there are several ways the competition for resources can take place. But besides the competition, in this sense, we are talking, there can be also other kinds of things. So more ideas?
Usually, sometimes the individuals can fight between each other, a direct competition, instead of just an indirect competition to go for a given resource.
Yeah, so fighting. Okay, so good. So what we are talking, the first thing we are talking, that there is it's non-observable, the competition for resources in the sense of the individual level, but at the population, yes, because you will see that the presence of one population depletes the second one, and vice versa. So populationally, it makes all sense. But if you want to be mechanistic and say everything I described as a population should be the result of some interaction between individuals, then this resource competition is not a direct interaction between individuals. So you cannot see it different from predator prey. Okay? So therefore, when we write models about competition of this kind, we are doing again phenomenological models. It's not scaling up from individual interactions. In order next week we will see how to do this better, because we can also model the resources. But then you need the resource, competitor 1, competitor 2, 3 species. Okay. So, but as it there's also a direct interaction called competition, which is fighting. Okay. So, but okay, why? Usually you could think that why would a species fight another species without being detrimental for her? I mean, the competition is still negative. Okay? So where are the benefits of fighting?
Resource, territory, because if the 2 populations are disputing territory, then have more resource, and this could be
territorialism. For instance, that's a classical thing. So there are resources, okay, and I just say, okay, nobody will touch anything that's reserved. That happens lots with some birds. Yes, they don't allow another bird to go to their territory. It happens a lot. You can see them clashing, and if you go just around. Okay? So they are just, actually they are competing for territory, which is also a resource if you want. Okay? But they do that by by a direct interaction. The competition is for territory, or for resources that are in the territory. What in this case? And classical example is an invasion of a certain kind of ant, of hormigas, in California, which was very, it's a classical example. So ant comes from Argentina, actually, has been introduced in California, and now there are only the Argentinian ones. The Californians have been away. It's classical, and you have all the invasion fronts, and you can study this. People have studied a lot. Okay, yes, good. Well, okay. So we will study this, which will be based on this phenomenological approach. So what we need is first, what's the mathematical setting? We need two populations. I will call it N1 and N2. Okay, and we will study the level of both population size of both populations, and we will try to write down differential equations, which will have to be coupled. If you are not a mathematician, what means this? You have an equation for, say, N1, okay, dN1 dt, that depends not only on N1, it depends on N1 and N2. Therefore, the influence of one population on the change induced in the first population. So, without interaction, we will suppose that the population is just growing logistically. Okay, logistic growth in the absence of competition. So I will start by writing this. Now things have indices. Okay, population 1, intrinsic growth rate of population 1. And then I have 1 minus N1 over K1, okay? And dN2 dt has some R2, 1 minus N2 over K2. Okay? So now I will want to put something on this side, which depends on N2 and gives a negative effect on this, okay? And the same thing, I want to write something here, which depends on N1, okay, which has a negative effect on this. So what I will do, I would do the simplest thing possible. I would just say that's linear, okay? Now, one way of doing this is simply saying, okay, now, instead of this, I will open up these brackets, and I will say, here, I would put something, it's a minus for all of them. Let me see how it has been written. Okay, let me, yeah. Okay. Yeah. So there's a minus here. Now I say, okay, N2 will also contribute to this. But the effect of N2 is not exactly the same of the intraspecific, it's interspecific. There must be a coefficient here, okay? It's not that one individual of the second species has exactly the same effects as the individual of the same species. There's some effective factor, okay? So what I would write in this case is like this, plus I will use a coefficient, which I call B12 and 2, like this, okay? I can put it with the K1 below. I mean, I could have not written this in this way, could written another way, but the usual way. And I will do the same thing here. Okay, this is minus, and then here, N2, B21, N1. So, meaning of this, B 1, 2 is the effect, is the strength of the effect that n2 has on n1. And B2, 1 is the strength of the effect that n1 has on n2. Okay? So you could think about the relative effects here. If, say, this is 5, it means that the effect of one individual of n2 has the same effect as 5 individuals of n1, if you want. Okay? Because n1 has also intraspecific competition. Okay? They are competing between themselves and with others. Okay? So now, this is called the Volterra model. Many people call it the Lotka-Volterra model for competition. It's common to say this, but actually this was written by Volterra alone, not with Lotka. Lotka is about predator-prey. Okay? Okay, now will come the mathematical part of the class, and we will try to see what is implied by this equation. So you would say, I want the solutions. Okay. We love to be like, I have an equation, I want the solution. I have an equation, I want the solution. But you can do it numerically. Okay? But we will do a quantitative analysis to see what is the implications on the long run for large time. I start with something, I want to know with the large time what will happen. Yeah.
That parameter, the V12, is adimensional, right? The V12.
B12 and B21 are non-dimensional, yes.
It's adimensional, yeah?
Yes,
Okay, thanks.
Yeah. Here, this is 1 over time, 1 over time. This is the current capacities and so on. Now, I will write again this equation. Let me write them large here. Let me write in a convenient way without so much. Oh, sorry, I forgot the n1 and n2 here, obviously. You all probably understand that I forgot this, yeah? I will write it this way, n1 over k1 and minus b12 n2 over k1. Okay, it's just to avoid double brackets here. Okay, and the same thing here. Okay, now how many parameters do we have in this problem? We have R1, R2, K1, K2, B12, and B21. Okay, 6 parameters. For every, you could think, for every combination of 6 parameters, I have some result. So I have a parameter space of 6. Okay, not so nice. Not so nice. Too many parameters. And that's the first appearance in the modeling practice of what I call the hell of parameter multiplication. Why? If you have, say, something more complex, many species, you will see the number of parameters growing and growing, and then you don't know the parameters, and then you cannot even advance much, neither even computationally. You will have to try all combination of parameters. It's a hell. Okay? So that's one thing when you go for more complex systems and so on. If you want that your system represents something which is in an age and so on, you better have the maximum number of known parameters that you can know. And in order not to have to do an analysis where you have to explore a large space of parameters in order to know the qualitative solutions of the equation. So here, fortunately, we have only 6, and we can make a little mathematical manipulation, and you had 6, and magic, you have only 3. So the magic is the following. It is absolutely arbitrary, but I can do the following. I will, let me put it in the good way. I can write down a new variable of time, which I will call tau, which is just the time times one of those. I can choose R1. Now, R1 is 1 over time in units, 1 over time. 1 over time times time is a non-dimensional time, okay? So that's arbitrary, because it's a constant. I can measure things in whatever units I want, okay? So I can do this. And I can do also something like this. I can say that I will introduce U1, which is just the population 1, referred to its carrying capacity. We have done this with the logistic, okay? A new variable I call U. And I have a new variable U2, which is just the carrying capacity referred to this one. Yeah? So, anything else? No, that's the parameters we have. We have 2 functions, n, and 1 independent variable time. Okay? Is everybody okay with rescaling? I'm just saying that if my population n1 is 100 and my carrying capacity is 200, then this is just 0.5. Okay? And if I want to go back, I say I want to go back to real things, I just have to take 0.5 and multiply by k1, and then I get back to 100. Okay? I can go back and forth between both. So I will do it step by step, because in the next classes and so on, I will just tell you, now we can find a non-dimensional thing, and I will give you the result, because I don't want to spend always half an hour making the calculation. So pay attention to this one, so that you won't be lost in the next part. Okay? So, okay. Now, first, dn1 dt will be what? Will be d dt of n of, sorry. So n1 is k1 times u1. I want everything in terms of u. So u1 times k1. Okay? And okay. Mu1 times q. Is it? Yeah, it's okay. But d dt, let me write it here. d dt is what? It's d tau dt, okay? Which is r1 d tau, okay? It's just, or if you want, if you don't want to use the chain rule, just think that you had d1 over d, and t is just tau divided by r1. The derivative is just r1 times d tau. Okay, so this is r1 times d tau of u1, and sorry, it's ugly. Okay. So you will have r1 k1 times d tau of u1. Okay? Good. There's the Q1 is constant. The time derivative, I can take it out of the time derivative. Okay? And then I have also that the time derivative to the new time derivative gives you R1. Okay? dn2 dt, the same reasoning. d dt of U2 times K2, because N2 is just U2 times K2. Yeah? And the time derivative is the same. So you will have R1 K2 GU2 d tau. Yeah? So pay attention. It's K1, K2, but it's R1, R1, because I have only one time rescaling. I don't have a time for each species. So the time, that's only one. So I use the R1 arbitrarily. You could have used the other one. Makes no difference. So that you get this. Okay? Now, that's the left-hand side here. Okay? Yet now we have to calculate the other line. Okay? So I will transpose the result here. R1, K1, GU1, G tau. And I write, let's start with the first one. And then I have R1. And I have N1, which is just K1, U1 times 1 minus, oh nice, this is just U1, okay? It's the definition of U1. Right? Minus B12 over K1 times N2. But N2 is K2 times U2. Okay? Very good. Now, magic happening. This goes with this, goes with this, goes with this. And I will take all this Gaia here and give it a new name. Okay? And the name will be alpha 1, 2. So looks cleaner, yes? Okay? All carrying capacities disappeared and so on. Yeah? So just then you could say, I don't know, what is the meaning of the thing? So the meaning is that this is exactly what we had before, but in new variables. The U is the population size referred to the carrying capacity, okay? And this one, alpha 1, 2 is just the B that you had before times this, K2 over K1, okay? But I call it alpha 1, 2, in some sense to simplify things, but also simplify the notation, but also because actually we are doing phenomenological models. So phenomenological models, as we will discuss, have this property that this is like the carrying capacity thing, okay? So you cannot know it beforehand. You know it after the experience, but it's not mechanistic, and it's not. Therefore, whatever. I mean, I didn't know from first principles B1, 2, and I don't know alpha 1, 2. So okay, all of these unknown things are just this coefficient. Okay, and now I do the same thing for the second equations. Okay, what with which K2 U2 1 minus, again this is U2 minus something which is B21 over K2 times K1 times U1, which again I simplify and call it alpha 2, 1. Okay. Now this goes with this, but this doesn't cancel with this. So I will get GU2 G tau is equal to R2 over R1, U2 1 minus u2 minus alpha q1 u1. Okay? And this thing I will call rho. It's the ratio between the intrinsic growth rates of both species. So, very good. Now, I will, let me put everything very clear. Okay, hope you are okay with this. Okay? It's just two logistic equations which are coupled through a linear effect between both species, which has, both of them have a negative sign. Okay, you have negative here, negative here. You see, if I wanted predator-prey, one of them would be positive. Okay, so and they are referred now to the carrying capacities and to this. I use the non-dimensional time, and we ended up only with rho, alpha 2,1 and alpha 1,2, 3 parameters. So we eliminated 3, okay, because we had 3 rescalings. Then we could eliminate 3 parameters. Okay, just a moment. I will end up with a problem here. So now we are ready to do the qualitative analysis of these equations, which now depend on 3 parameters. Okay? I will therefore rewrite them, and I will forget the derivation, and now we want only to think about them. Okay, let me go here. Okay, that's what we had already. Now, we want to do something similar as we did with the single species when this dynamics, when it was more than the logistic, when you had all those fixed points analysis. I want to know in this case, I want to know the fixed points. Fixed points again, it's just jargon. It's fine n1 and n2, such that they won't change in time. That's the equilibrium. Okay? I want to find the equilibrium. Okay? And then I will ask myself stability of equilibrium and so on, which can be done mathematically, but we will do it graphically. If you want it more mathematically, you take the book of Murray, and it's done with Jacobians and everything that you want. Okay? So fixed points, therefore, are the population levels such that these guys are 0. The derivatives are 0 because the population is not changing. Okay? If this is 0, the fixed points have to obey this equation. Yes? Equals 0. Okay? If this side is 0, this side is 0, and this is an algebraic equation where now u1 and u2 will be constant in time, they are just numbers, okay? And these are the population levels of equilibrium. Okay? The rho disappeared. Further magic. Okay, if this is 0, I can put a rho here, but if rho is not 0, doesn't care. Okay, it's a non-zero thing multiplying something that has to be 0, so I can't forget. Very good. Rho disappeared. We have only 2 parameters. Better and better. Okay, and what we have the only parameters that are the competition parameters. The carrying capacities have been scaled away, and the intrinsic growth rates, which were encoded in rho, went away. Why? Well, we go to we want to know the steady state at fixed points. Populations don't change, therefore there is no time scale associated. And so rho disappeared. Okay? Good. Now, this has 4 solutions. Okay? There are the trivial one. Okay, let me write here. First one is just n1, u1 equal to 0, and u2 equal to 0. Because it's 0 here, it's a solution. Okay? But we don't want this solution to be just the only one. And then I can say u1, let me just follow exactly what they have done. What? No, okay. Usually, people in this case put sometimes a star here, okay? Meaning that's the fixed point. It's not just, okay? I want to use it. In the books that they use, in the books of Murray, okay? But we understand that we are looking for the fixed points. In order not to have a too heavy notation here, I won't use the stars. So it could have, meaning the stars means that's the particular value of the function u, not the initial condition or something. Okay? So I can have also this one, which is this guy equal to 0, and this guy here equal to 0. So if u2 is equal to 0, in order to this guy here in the brackets to be 0, this is 0, because it's u2, then u1 is equal to 1. Okay? Everybody's okay with this? And the 0 is always a solution, and what remains here is either this one is 0, which was the first case, or as this one is already 0 because u2 is 0, then u1 is equal to 1, and then I can do obviously the symmetric case. Okay? The symmetric case will be just u1 equal to 0, u2 equal to 1. And then I have a fourth case, which is neither u1, neither u2 are 0. Both populations are different from 0, and you have to solve this. This equal to 0 and this equal to this. Are linear equations. You can isolate u1 in terms of u2. You can substitute it here and find solutions. That's just linear equations. I will write down the solution. Okay. So these are the 4 solutions. Now we want to know, I have 4 solutions. I will ask myself, so now say I start with an initial condition, population 1 of certain size, population 2 of certain size. Which of the fixed points it will go? Okay? Where will it go? So that's not answered. This will depend on the stability of these guys. Okay? Just a remark that obviously we need that this here is different from 1. Okay? Alpha 1, 2 times alpha 2, 1 has to be different from 1, otherwise you have a 0 here. Okay? Very good. So now let us do some graphical analysis. And I will draw 4 diagrams. And today I'm happy. I will only need to draw lines. I don't need parabolas, and so therefore the picture will be much more closer to what it should be. Okay? And I will mark. So, okay, these are what we could call, if you want, it's not a phase diagram. Phase usually refers to GNDT. Sometimes people also call it phase diagram, whatever, configuration diagram, whatever you want to call it. Okay? So I will mark the points 1. Let me see here. In both axes, which is when the carrying capacities, okay? Just now clearly this one is unstable, okay? Because if populations are very small, then this term U1 and this term, both of them are small in respect to 1. Therefore, that will give you here a positive growth rate, okay? So this one is always unstable, okay? As it was with the other models, like the logistic. Okay, this one has always, you don't have Ailey effects. If you have Ailey effects here, you would have something very different. Okay, so near 0, if I make a small perturbation near 0, I have small population. U1 and U2 are still small with respect to 1. Therefore, the growth rate here, which is a positive, both of them are positive, and the population grows. Okay, so this one is okay. So now let me proceed in the following way. So I will draw what is called the null clines, which is the lines, null clines. With K or I don't know, null clines. Let's see. So, which are the lines where the populations are constant? Okay. So one obvious case is always that the 0. I mean, I don't need to draw the 0. Okay. And obviously, this is one fixed point here. This is also one fixed point here. Okay. So I will draw the first one, and let me follow exactly. So everything will depend whether alpha 1, 2 or alpha 2, 1 are larger or smaller than, bigger or smaller than 1. So let's start with this case here. 1 over alpha. Let me mark this point here. Just 1 over alpha 1, 2. Okay? So this point will go, one of the lines will be this one. Okay? This is the line where, okay, this is the one which makes this guy 0. Okay? So if this line here, okay, 1 minus U1 minus alpha 1, 2 equal to 0, okay, it's a line, okay, and U2 is just given by, I mean, this is the line which describes this linear equation, okay, so it goes through n2 equals 0. Okay? When n2 is equal to 0 here, n1 is equal to 1. And when u1 is equal to 0, u2 is 1 over alpha 1 over 2. Okay? But now you could have it larger or smaller than 1. And I'm taking this first case, okay? So this is the line where I will call, just for, I will call this expression here F1, okay? And I will call this expression here F2, just to have, so this is F1 equal to 0, okay? Now, I will take the second case where, okay, now, there is also a line which will be the line of F2 equal to 0, which will go from 1 to 1 over alpha to 1. Let's check. Okay, this equation here. If U2 is equal to 0, here, to 0, and U1 has to be 1 over alpha to 1. And if U1 is equal to 0, then U2 is equal to 1. It's at both, we have 2 points, we have just the line between the 2 points, okay? So, now, what does it mean? This has an intersection here, okay? Yep. And we could try to see what happens here. So, this, we know, we will now draw little trends, okay? We know that here, if I'm here, population 1 and 2 are growing, okay? So I will show it like this. Both are growing, okay? Now, when I cross this line here, I cross the line F2 equal to 0. It was positive. If I cross the 0 line, it has to be negative. Therefore, here and over this line, you have tendency to go to decrease. Okay? Okay? I'm just, these are the lines where there's no increase and no decrease. Outside the lines, there's either increase or decrease. So I'm using the fact that if I start here, I know that both are increasing. When I cross the line, I have to change the sign. Okay? So the second case is an F1 is equal to 0. When I go this here, and I cross this one, okay, I will alpha to 1. Let me pay attention. Yeah. Okay. Okay, again here. When I go, this goes down, but still it goes, you didn't cross F1 equal to 0, so they have this here. Okay? It goes, increases in here and decreases here. And now it will change sign, then both decrease here. So you go on playing with this, you will have this one here, you will continue to grow here, because you didn't cross this second line, this line, but you will go up and here. And here you will go to down and this way, okay? So now the fixed points are this one, this one, this one, and this one, okay? The other ones are not fixed points, this one, okay? Now, you see, if I start here, I will go in some trajectory like this. Both of them, U1 and U2, growing. And then, at a certain point, I will have when I have crossed this line, I have a tendency to decrease one of them and increase. Therefore, that would be something like that. Okay? This one starts to starts to decrease. It's not only lines, okay? And will give you this tendency, okay? If I go this way, okay, I will start to increase. I still increase here in this direction, but I go in this way. I will not will end up at the middle. Okay, I end up at the middle. I could start somewhere else also. If I start here, for instance, I decrease both. Okay, but I'm decreasing, but then this one starts to increase. And you go again, increase. Okay, you will increase here. Okay, and then you will go this way. From anywhere you go this way, so I would say this one. This is a stable fixed point. Okay. This one. Okay. And the conditions is 1 over alpha 1, 2. It's bigger than this. 1 over alpha 2, 1 is also bigger than 1. Okay. Because now we will do the same thing, but I will take the case where this is still the same thing, 1 over alpha 1, 2, but the 1 over alpha 2, 1 is on the other side of the 1. Okay? So I go on and draw again the same lines. Okay? But in this case, they don't cross. They don't cross anymore. Okay? So there's no coexistence. And now the fixed points I can have is 0, which we already know it's not. You have these 3 possibilities. Okay? Now you ask yourself, well, this one analysis again. This one is f2 equal to 0, which is the null Klein associated with this one. Okay, and this is and this is f1 equal to 0. Okay, and hope I do the correct drawings. I already lost everything here. So, this one here, in principle, you start with both positive. You cross this, then this is the null Klein for variable 2, which appears here. Therefore, you will change sign of the here again, like that, but still like that. Okay. If you cross this one, it will be the same thing. It will go in this way. Okay. But then if you try to cross this one here, you change. Okay, you go back this way. So you go back this way, and you still are decreasing. The same thing here. If you go here, you are decreasing here. You got here, then you will go here and will be also decreasing here and decreasing here. You will end up here. Okay? Therefore, this is the fixed point. This one. Okay. Sorry, this one.
Professor.
Okay?
Sorry, I think I understood the null lines concept, but I don't get why the line, for instance, needs to go from U to 1 to 1 divided by alpha to 1.
This is still, let's say this one, for instance, okay? So you need this to be equal to 0.
Yep.
Okay? So this is a line. It's a linear relation. Okay? In order to draw a line, you only need 2 points of the line. Okay? So 1 point is okay. This was like this. Okay? Now 1 point is clear. You take the zeros, the crossings with the axis. So I take u1 equal to 0. Okay? Then you have to have u2 equal to 1 over alpha 1, 2. Okay? That's one point of the line. 0, u1 equal to 0, u2 equal 1 over alpha 1, 2. That's one point. Second point, I take this one equal to 0. And u1 has to be equal to 1. So u1 equal to 1, u2 equal to 0. Those are 2 points on the line, and I draw. I mean, one of them is, let's say, one of them is this one. Here, the other one is this one. I just draw a line. And this is the line where is F1, which is what drives population 1, is 0. Okay? And so therefore, from one side of the line, it's positive. On the other side of the line, it's negative. Okay?
Okay, thanks.
Okay. So, I did a mistake here. So, what will happen is that, you see, this point is clearly like this. It is stable, okay? And it's pointing down because you have already crossed this, okay? A little bit of, give a little bit of thought. This one is obviously unstable here, okay? So this is the case where the fixed point is equal to u1 equal to 1 and u2 equal to 0, okay? That's the fixed point, and it's valid if 1 over alpha 1, 2 is larger than 1, but 1 over alpha 2, 1 is smaller than 1. Okay? This is elimination. One, and at the fixed point, there's one population which is at the carrying capacity, and the other one which is 0. So therefore, I can say that in this case, U1 is the best competitor, and he wins the competition, eliminating the second species. In this case, I have coexistence. Okay? Now, yeah.
I understood that this one is elimination and the other one is unstable, but I don't know.
Which other one? This
like
one?
Yeah.
This one?
This one.
Okay, so here, what you have is this one, you look always at the lines, okay? So this is the line, which is F2 equal to 0, okay? So you would have something like that. You cross it, you would have going down. But if you get here, the sign of U1 takes you away from it, okay? Therefore, it's unstable. It doesn't stay there.
Okay, and I don't understand, like, biologically, what is the difference? Like, the alpha is different?
What?
I'm sorry, I just don't understand, like, for example, it's elimination, but why this one eliminates and the other one doesn't?
No, so that comes, where is our competition? Our competition in the coefficients of the force of competition, which are alpha 1, 2 and alpha 2, 1, okay? So if they obey this, okay?
Oh, okay.
Okay, if they obey this work, it's different from this one. If these are both, okay? Larger, okay? If they obey this one, this inequalities, then you have the result that one eliminates the other one.
Okay, I understood.
So now you can do this obviously for the symmetric case here, if you want to put it like that, like this, 1 over alpha 2, 1, which connects with this one, and then you can do here 1 over alpha 1, 2, which connects to this one, which is similar to this one, just that you have now, this was F1 equal to 0, F2 equal to 0, now it's inverted, and everything gets inverted, and I want to again all the thing, but this one will get fixed point will be, and then this one. This one will be the fixed point, which is stable, and this is unstable. Yeah.
Yes, in the first diagram, the point that is in the intersection between the lines are the number 4, right? The number 4, the fixed point number 4.
Yeah.
Okay.
Okay. So this is valid if 1 over alpha 1, 2 is smaller than 1. 1 over alpha 2, 1 is larger. Okay? So you see that if one of them, because you can also obviously say that alpha 1, 2, you could multiply it, okay? Now, if one of them, of these ones, one is larger than one is bigger than 1, and the other one is smaller than 1, then you always get an elimination, okay? So this will give you which one is the best competitor, okay? It's the strongest competitor, okay? And it's also natural to think about this, okay? If this say the influence of 1 on 2 is very strong, and the influence of 2 on 1 is weak, that would be this one is somehow much more important than this one, okay? And this is what these fractions there say, okay? Well, then there's a fourth one, but we won't have time to discuss it fully, but and I leave it for maybe you can. In this case, I had something like that. 1 over alpha 1, 2. And I put it here, 1 here, 1 here, 1 here, and 1 over alpha 2, 1. This one connects here, and again here. So you have another point here. You have this one, this one, this one, and this one. And if we have maybe have time, maybe on Friday, we can do it again and give you as a challenge to show that this one is stable and this one is also stable and this one is unstable. Okay? Both of them are stable and this one is unstable, which will give us connection for Friday to discuss what is going on here. Okay? You have two stables. Here you have one point that is stable. Here you have only 1 point that is stable. Here you have only 1 point that is stable. Here you have 2 points that are stable. Therefore, that will pose the question that when I start a certain population, which point I will arrive. Okay? So, okay, this will take a long time to discuss now. We will put it for Friday, okay, to discuss what happens. So this is called a bistable system. It will be very interesting for other discussions in the future, okay? Anyhow, what we get here is that the result of the competition is mutual elimination, except if competition is weak. And weak is this case, okay? That's when you have coexistence. So if you write this again here, let's say, let me put it here. This means alpha 1, 2, okay, is smaller than 1, okay? And alpha 2, 1 is also smaller than 1 here, okay? I'm just inverting here. Yes, this means that these guys here are smaller than 1, means that the interspecific competition is weaker than the intraspecific competition. You have a 1 here and you have something which is smaller than 1 here and smaller than 1 here. Okay? In this case, you have what you call the weak competition. The effects of competition are weak. And then you can have coexistence. If not, if one of them is smaller than 1, then the effect is stronger than the effect of the population on itself, and then you have this kind of eliminations. Okay? So, this is a very important result historically, which means that unless you have reasons to think that the competition is not strong, you will have the elimination of one of the competitors. So what would be the idea of competition is not strong? Okay? How could competition be stronger or weaker ideas? There and there. Mike.
Not that strong when you have generalist species that they compete for a resource, but they have other resources.
Yeah. So, okay, other ideas?
When the two species are very different in terms of their relation in evolutionary time, they might use different resources and the competition is less strong.
Yeah, so this would be the difference between the... We are not modeling the resources, okay? And then that's where all the mechanistic discussion goes, okay? So we have thrown away. So at the level of phenomenological population size, and at the phenomenological population dynamics, like this, at this level, population, weak population has to do with that the common resources are not so essential. Maybe there are some common resources, but you would think about the following. If they had both exactly only one resource, and they would compete for this only one, this should be strong competition, okay? Because they will, will grow, and and then they really compete, because if they start growing, then this thing grows here, okay? This part, okay? Then one will deplete the other, okay? Whereas if it has maybe some other kind of resource, one of them has 2 resources, the other one has also 2 resources, and they have one in common, but they can always rely on the other ones and so on, and then you say, okay, that should probably not be very strong competition. So that would be. So this brings us to the idea that if two species have exactly the same resources, they cannot coexist. Okay? If they have exactly the same resources and the same reliance on the resources, in that case they cannot coexist. Okay?
There is also the case where the two species are not really limited by their shared resource.
Oh.
So, for example, space, but they are already limited by how much food they can get. So space that competition won't really matter to the dynamics of
exactly. So now you're understanding how the play is. Now the importance of this result. This is a result from very seen at very important researchers. Is Georg Gause. Gause is a Russian biologist, and he wrote a book in 1934, actually in English, because he could not publish the things in Russian at the time. And remember Raymond Pearl, the guy with the Drosophila, so he published the things for Gause, and this became known as the principle of competitive exclusion. Okay, Gause, you have online the book of Gause. It's very nice, okay, because Gause did not only do the math. The math actually is Voltaire. Some years ago, earlier, he did experiments. Okay, so it's a very curious book because it starts talking about something completely different. It starts about epidemiology of malaria, something Ross McDonald model, an epidemiology of malaria. So, and then he comes just to the, because how's the book called? The struggle for existence. And you want to quantify this somehow, the struggle for existence. And then he starts with this and they say, you see, with all this data from the field and so on, I cannot do anything here. Therefore, okay, I discussed this, but I now go for lab. So he defends it and we like, go to the lab. And he made experiments with protozoa. Okay? And so he made a famous experiment. I will just show you this here. Come on. Huh? Wait, oops. Where did it go? Ah, okay. Let me put it larger here. Well, maybe I have a problem here. I don't know. It's warming up. Okay. Okay, it was. Okay. Now that's warm. And so, maybe you can go to the full. So what he did, he had two protozoa. He could grow them in cultures in the lab. So he had this species, which is Paramecia. Okay, Paramecia. Paramecia is the plural of Paramecium, and the species is Paramecium caudatum and Paramecium aurelia. So what did he do? He did a typical competition experiment, which is I grow separately in culture. I grow Paramecia aurelia, and I grow Paramecia caudatum separately. And so they have been grown. Here you have aurelia. Okay, I don't have a pointer. But you see the points separately, it goes up and ends up here, okay? Now, separately, caudatum goes also. So they go to their carrying capacities when they are separated. Then you mix, okay? You mix, and what happens is when you have the mixed population, Paramecia caudanium still grows a lot, and goes to a smaller volume, but is not eliminated. And while you have initial growth of Paramecium caudatum, and it goes down and is eliminated, or at least almost eliminated here. Okay, so that's typical population, typical situation where you have competitive elimination. Now, here it's interesting because we have not only the fixed points, we have the dynamics. So you could ask yourself, well, why is Paramecium caudatum initially growing? Paramecium caudatum is initially growing. It grows and then it goes back. Why? Yeah, so competition is probably weaker here because the size of the population of Aurelia is smaller, and then we have the math for this, okay? If this population, say Aurelia is population 2, okay? So if this is small, even if this guy is important, alpha 1, 2, in the first part of the dynamics, this one is small, then this effect is not very strong. Okay? And therefore, all of this is still positive. Okay? And you grow. Okay? Actually, and then this becomes this population of Aurelia starts to increase to a point that the competition becomes strong and caudatum gets out because it's not strong enough, let's say, in competitive wise. Yeah. So in somehow it is also an instance of the RK selection. It's not very pretty much selection, but you can think that Caudatum might even be a better R competitor, R selected, because it can grow fast. Okay? Although also Aurelia grows fast, more or less. Okay? But actually, if you look, it's like, I mean, it starts even growing a little bit faster than Aurelia. Okay? But then Aurelia is K-selected in this case because it's competitive when you are at high densities. It's competition, and K-selection was exactly being good at competition. For Aurelia, at the end of the whole thing, which is you get what was the K-selected species. So you have a kind of small example in lab of succession, more or less. Okay, and so just to finish the discussion, that there was something very interesting, which, if you read the book, it's just some lines later of that. He made it again the same thing, but day after day, Gauss cleaned up the metabolic waste of this that the species leave in the medium. It cleans up the medium of the metabolic species. Okay? What happened is that Paramecium caudatum wins the competition. Why? Because, well, Paramecium caudatum in principle seems to be maybe a better R at reproduction, but it actually what happened here is it loses competition, but you don't know the real mechanism. So the mechanism is that Paramecium caudatum does not support pollution, and Aurelia pollutes a lot, and therefore caudatum it's out of it. Okay? When you take out the pollution, and I don't know how to explain why caudatum is better in clean things. Neither Gauss tries to discuss this. But then you don't have the pollution, which was the way of the competition was going on. Then you have, in this case, caudatum. We don't have a plot equal to this one. It has a very complicated plot that I don't understand. So you see, environment is very important for competing species, and not only competing for all predator prey. So environment may shape the forms of competition. Okay? This kind of reasoning took, this kind of competitive elimination later took the form of defining something what's called a niche. A niche is something there has been a lot of debate, and it's a little bit outdated today, but it's incorporated into the normal ecological thinking, which is maybe I have a multidimensional niche, not only one resource. I have several resources. Okay, I need light, I need water, I need whatever. And then there's other guy that has also a niche, which is not the same, but has an overlap. Okay? So if this overlap is important, then you have this kind of elimination. And then, and if it's not important, if the overlap is not very large, then you have the possibility of coexistence. Okay? This comes from speculations about a good question which was posed by Hutchinson, the guy that wrote this book here, which is, why are there so many species if they are going to compete, and there should not be so many species at all, but we have a lot of species here. So that cannot be exactly true with the Gauss story. I mean, that he has a point that the competition is strong, then you get eliminations, but why do we have so many species? Right? And this shaped a lot of the ecological theory in the sense that instead of looking at nature and just saying, okay, they coexist and so on, when you see them coexisting, you have to explain coexistence. What is the mechanism that explains coexistence? that's an example of how theory shapes also and the experiments that you will be looking for, because now you are interested in you have a theoretical framework which tells you that you expect competition to create eliminations, and when it doesn't, there's some mechanism which is coexistence promoting. Okay, so there are many of them. Okay, many. Like we didn't at all take into account space, use of space. Okay, maybe the best in restricted space. There's one that has maybe better abilities to compete, has a better consumption rates on something, but the one that would be the loser isn't because it can coexist, because, well, maybe it's good at explorations. Maybe it can explore space, say, more quickly and get to the resources before the other one arrives. When then the other one arrives, it gets eliminated, but it keeps going on. Okay? So this is one possible mechanism. The other possible mechanism, obviously, is many resources and so on, also like this. Okay, and there was even there's a marvelous paper, also by Hutchinson, which is the paradox of the plankton. Okay, if you take a book of water and have with planktons, you have thousands of species. Okay, but planktons, if it's phytoplanktons overall, if it's phytoplankton, they only have as resources oxygen and nitrogen, phosphorus, or some 6 or 7 or 10 elements. And so you want to say, I should have only 10 species that have thousands. And I can even enforce competition. I can deplete the resources. So I think, okay, you just say there's coexistence because there are plenty of resources. Okay, cut the resources. You go on, you put them into water which has less and less resources, and they continue to coexist. So it's not a paradox, actually. It's just a fact. Okay, people in ecology like to say paradoxes to things that are actually not paradoxes. Okay, well, but you couldn't. So, and this also created all the discussions of why you have coexistence in nature and so on. All of this is driven by the idea that competition creates elimination, which to some extent is also the basis of natural selection. Okay, and if you know that there are natural selection, it has been very well documented by the time of middle of the last century, then you know that there are some basis of saying that competition creates elimination. There is some basis, but on the other hand, you have there are so many species and so on. Okay, so this is the tension that really was the heart of the 20th century ecology, like until the 80s and 90s. Okay. Very good. So that's it for today. Tomorrow we will continue, but we will go to predation, and I will leave a discussion of more complicated cases of competition for Friday. Okay, don't forget, you can write down some questions. Okay, that we didn't have many last Friday, but I look forward to having many this Friday. Okay, so thank you for.